Hi, in this video, we want to take a look at Bayesian models for item response theory. Now, right now, I'm at Skydive to land. I was hoping to jump today. I was really excited, but as you can see behind me, it's too cloudy. I'm really disappointed, but hey, at least I get to do some statistics, do some psychometrics. So it's going to be a beautiful day regardless. All right, so in item response theory, what we've got going on is that I want to use under the hood latent hidden variables to model like proficiency on individual questions on a test. Okay, so we're going to call the variable that we're using as a predictor. These are going to be these will be latent variables. We're going to estimate these using factors. So a factor is an estimate of a latent variable. And we can think of it similar as like principal components in a way, because there's a mathematical like relationship there. Now, when we are doing the item response theory, we're going to call each question an item. And why do we call it an item instead of a question? Well, because at times what we want to do is maybe it's a survey, maybe it's a psychological measurement where there isn't really a right or wrong. Now, if it's a test, a quiz, something like standardized test, then there's right or wrong, and the term question makes sense. But item is basically just something that we're evaluating on. It could be a question, it could be like a scale of like dislike, something like that. Now, in this video, we want to talk about going the Bayesian route with this. All right, so there's two schools of thought in statistics, two major ones, I should say. There's a frequentist, which is like classical statistics, and there's a Bayesian. All right, so the frequentist point of view is, in a gross generalization, is I just let the data speak for itself. I don't incorporate any previous information. All right, so this is great if I don't have other information to pull in. This is great, so if I'm just naive on what's happening. And something that is nice about this is that I know that I'm letting my data speak, and I'm not biasing anything with my personal beliefs beforehand. Now, a disadvantage of the frequentist point of view is that I can have subject matter knowledge, and if I just let the data speak 100%, then I'm not incorporating like what I already know to be correct. Also, if there's flaws in my data, I have no buffer to really prevent that from pulling my model away from what it truly should be. Now, the Bayesian point of view, the idea is that I have some prior understanding. So the word prior is important. The prior understanding what's going on, and I use that prior information to develop something called prior distributions. Those prior distributions are statistical distributions, probability distributions of what I believe to be correct on the parameters in the system. And then what we do, we pull in some data. So I take my prior distribution, I take my data, I put them together, and that gives me my posterior distribution. And the posterior distribution, as long as these like agree pretty well, is going to be a lot more informative than what I had beforehand. Now, when it comes to a question worrying about biasing my results, something that you could do to protect yourself if you're doing Bayesian statistics to protect yourself from being biased is choose prior distributions that have high variance or low precision. And there's basically like a sample size and precision aspect to our modeling, that the two of these, the more precision I have here, the more influence the prior will have on the posterior. The more data I have, the more influence the data will have on the posterior. And it's kind of like a balancing act between the two for the output. All right, so now let's get specific to item response theory. This example is taken from Modern Psychometrics with R by Mayer. It's a Springer textbook, and here's the GitHub page for the code that I'm using. And I'm modifying the code just to emphasize things a little bit different. And to make the code consistent with my personal preferences on how I write my code out. All right, so for this, we're going to be using the MMC pack, so Monte Carlo Markov chain pack for this. So this is really nice. And what this does, this takes care of a lot of the Bayesian statistics for us. We don't have to do anything with bugs. We don't have to do anything with JAGs. If you don't know what the bugs and JAGs are, don't worry about it at this point. Now, a disadvantage of this is that since this is taking care of so much stuff for us, we lose a lot of the flexibility. So if you're someone who knows what bugs are and you know what JAGs is, from doing Bayesian statistics, you may not want to use this one. You may want to roll up your sleeve and dig into modeling yourself. All right, so the MMC pack gives us unidimensional models. And so here we have 1D models and a hierarchical 1D model. We have multi-dimensional models, and so here we have going off of heteroscedasticity, and we have robust, and then we can also have dynamic. So dynamic is where our parameters are changing over time. When I have if I give subjects the same items over and over, I can use, let's say 5 times. I can use all 5 measurements with a dynamic model, because there I'm measuring how personal parameters change over time. All right, so something about the MMC pack that we need to know about is that it takes standard normal priors for the person parameters, our thetas. So it's using standard normal. And for item parameters, it's using normal priors with mean 0 and precision 0.25. All right, so if I feel like I have strong belief on what's going on, I can change this up. I can change it so that if I have really strong belief in what's going on, I can set the mean of the prior where I want it to be, and then increase the precision quite a bit. If I don't have a lot of faith in my prior information, then what I can do is I can reduce the precision to be very small. And now, something that's nice about this is that if I do Bayesian statistics, I get a very complete representation of what's going on. And if I go with a low precision prior, so I am incorporating some information in, but I get a very complete representation if I want to roll up my sleeves and start really digging into it. I've only used that for very specialized projects personally, but it's there, it's available. Bayesian statistics offers tools that I have yet to see elsewhere. All right, so we got 2PL models estimation, and so for this example, we're going to go ahead and use the questionnaire for our package authors. And it's a data frame with over 1,000 individuals and 18 items involving job complexity, information processing, problem solving, variety of skills, and specializations. So this is digging in on what motivates people when they're making our packages. All right, so let's go ahead and load the data. So the data set is coming from the MPsychoR package. I love saying MPsychoR. I think it's kind of entertaining. Now, one thing I do here is I filter out the times that I have all missing values in a row. If I have all missing values, the observation is useless. Let's go ahead and just get rid of it. All right, so to start out, what the author does in the textbook is the author takes the non-Bayesian model, the frequentist model, and then uses that to get an idea of what the coefficients should be. Morally speaking, this is not Bayesian statistics. So if you are a purist, you will, your head would explode that this is not what you're supposed to do when you do Bayesian statistics. The goal is always just to create a good informative model. So if I don't personally have a problem with this. I think this is a good approach to make sure that when you get your Bayesian model, you have everything that you actually intended to have, you have the right structure you're looking for. Because what I like to do, I generate the frequentist model. I look to see at the details of basically the structure of it and the shape to make sure that when I go through and I start manipulating the JAGs, I am getting what I actually intend to get. That's my personal use. I usually do not use a frequentist model for my parameter estimation at all, though, because I try to be consistent with the the like purest view of Bayesian statistics. And so here we're taking the LTM package and we're using the LTM namesake function. Now something about this is that it needs the GH matrices. This is like a data set inside the package floating around. If I don't actually load it manually, it won't be available. So on this line here, I'm grabbing that data set just so the function can reference it. And so after I build the model, oh, okay, so something about this formula is saying the entire data set depends, I'm going to model it based off of one latent variable, one factor. So in this package, I've got the choice of two possible latent variables, Z1, Z2. I could use them together, and I could use an interaction model if I choose. Here, we're just going with one. So our model is going to be, our models will be for each individual item, logistic regression with a slope and an intercept term. The slope will correspond to the discrimination parameter, and then the intercept will correspond to the difficulty. And here we can see the output. So this gives me a good feel of what I should be getting from my model, at least in terms of structure. All right, so now let's go ahead and build the Bayesian model. All right, so something we're going to do is that we're going to do this 3 times. Why are we doing this 3 times? Well, with Monte Carlo Markov chains, I have to do random number generation. And so if I make a poor choice, let's say I only build one model and I make a poor choice, I can get things to be pretty bad. So what I'm going to do this multiple times, and I'm going to proceed from there. If things are jive and things are consistent among the 3, I could be relatively confident that I've got the right results. Now, something about Monte Carlo Markov chains is that they take a bit of time to converge to what you actually want. And so what we do, we have some iterations that we call burn-in. All right, so in the Markov chain aspect of a Monte Carlo Markov chain, basically I take an iteration and I use that iteration to get another iteration. I use that iteration to get another one and another one, and so forth from there. Now, the random number generation is where the Monte Carlo part comes in. Well, with the iterations, if it doesn't get to the right distribution yet, then it's a crap value. I don't want to include it. So what we do is we do a bunch of iterations, with enough iterations I believe that I don't have to worry about convergence issues any longer. And what we do a bunch of them, we throw those out and we take everything afterwards. The ones that we throw out, we call burn-in. The remaining ones, we keep. So here, this is going to generate 55,000 iterations, and each of these will be considered an estimate. The first 5,000, I have questions about their validity in terms of convergence, so I just throw them out. I don't even look at them, and those are the burn-in. The remaining 50,000 I keep. Now, I set the seed because I want this to be reproducible, and here I'm setting what do I think the intercept and the slope should be in the logistic regression models. Here I'm setting the precision for the parameters, so we're not using the default values there. And then I'm setting verbose to false because it will give me a lot of outputs, and frankly I only care about the very end in most cases. I just want to know that things converge at the end. I don't need each individual step. And we repeat this where I change the random number generation seed. So first one has 1, 1, 1, second one has 2, 2, 2, third one has 3, 3, 3. I'm using the same starting values every single time. And then I put this all into a special list format. And so putting it into a list makes it easier to work with, easier to iterate. By putting it into an MCMC list, I have additional functions I can use to execute to make things easier for me to interpret. And so what I'm going to do after it's in the special list format, I'm going to plot and take a look. Do I feel like this is a good model from the output, from the diagnostics? And I'm just going to look at the distributions first. So here, If I see like a slope going, or if I see that it's still like, it hasn't like flattened out and stayed flattened out, I don't trust it. So if I saw like something like flat, then flat like this, then the first ones I don't trust. Also, if I see that there's a slope shape in this plot, I just don't trust the whole thing. So here, everything is flat. So these are all the ones so the black is going to be from the first iteration, red will be from the second model, green will be from the third. And it's a lot of iterations, a lot of overlap. I would actually go through and look at additional output before I would trust it. And now here I get my posterior distribution of the alpha. And then here I get the posterior distribution of the beta. So something to notice is 0 contained in the realistic interval. So it's not a confidence interval, it's called a credible interval. But I want like the 95% most likely probability interval off of the distribution. I notice that 0 is not in there, so I conclude from a hypothesis test point of view that the parameter is not equal to 0. And now here, I see that 0 is in there. So if I'm doing a hypothesis test, I'd be like, beta might be 0 on this one for this individual question. So realize that this is question with label 22 on there. And now I go through and I get output for every single question. I consider the convergence, and then after I consider the convergence, I decide is it a good or is it trustworthy or not. If I feel that it's trustworthy, I go down to the distribution and I start taking a look. What do I feel like the value is? And we can just keep on going, and there's just tons and tons and tons. Now you'll notice that there are times that it has the beta, but it doesn't have an alpha. All right, so for 23, if I look here, sorry, I misspoke. We have the convergence aspect, and then we have the distribution. We have the convergence aspect, and then we have the distribution. I just keep on looking through until I, reach the conclusions I need. And there's a bunch, so for every single question, I'm just scrolling through this pretty fast. All right, so now let's take a look at a dynamic model. So for this, the dynamic model is that I've given the questionnaire to the same people multiple times. For this example, 5 times. And what I want to do, I want to know, how do things change? So what we're going to do, we're going to use one latent variable, which is estimated with a factor, and we're going to take that, and I'm going to see how does it change over time. And if it, I'm interested in each individual, but I'm also interested in the population as a whole. So what we're going to do, we're going to take the health risk behavior. So this data set asks middle school and high school students about health risky behavior involving smoking, drinking, and marijuana. And it's given 5 different times. And the questionnaire is 0 is never, so that'll be a less risky behavior response, and 1 is at least once. And there are 538 individuals in the data set, and there's 4 individual items. So 1 for smoking, 2 for drinking, 1 for marijuana. All right, so let's go ahead and load the data. It's once again from the MPsychoR package. Now, if you look through, there's a lot of students in this that have all zeros. Well, if they have all zeros, I was working with the full data set, and I was having issues with having it converge. So I'm going to change the data set to only those who have 1 or more, at least 1 response. So these, the data set I'm restricting to are the ones who have at some point on the questionnaire said that they had risky behavior. And now I want to go ahead and visualize it so I get an idea of what's going on. I'm going to do some bar plots. So what I'm doing, I'm reshaping the data through all of this using the tidyr package. And I'm doing some data prep to make sure I get the values I want. And then I go ahead and I plot it. And so here, this is all ggplot code for plotting the upcoming plot. And so here, we can see how frequently did a student say, I have at least once of the following items. All right, so remember, this is restricted to only students who have at least one in their row. And I can see the bar plot. So you can see as time goes on, we get more red in all categories. So that's something that's important to notice, that when they say at least once, it's going up with time. And we can also see that like cigarettes is relatively low compared to the others. The second alcohol is low, and the first alcohol is probably the most frequent of all of them. All right, so now I do a little bit of data prep to get everything set up for to be able to connect my data set with the time aspect. So let's go ahead and build a dynamic model. Now here I'm going to be using the Monte Carlo Markov chain dynamic item response theory one-dimensional model. I'm passing my data. Now here I'm specifying the time feature to it. So I have to give a vector for the times. And we're going to be doing 20,000 observations after a 5,000 burn-in. I set the seed, and then I'm going to store the ability, because this is what I'm actually interested in on this one. How does the theta change over time? How does the person parameters change over time? All right, so now after I've built the model, and this took a little bit of time to converge, something to be mindful about with Bayesian statistics, that Bayesian takes a long time to converge frequently. So if you are under the gun for time, Bayesian might not be the way to go. If you have the option, use a conjugate prior if you're under the gun for time. Here, it's not a realistic choice. Because of how complex things are. All right, so let's look at the posterior mean. So here, I'm going to take the summary function to extract the posterior averages. And so remember, I took my prior of normal distributions, I take my data, put them together, I get my posterior. Now, this is incorporating my subject matter knowledge and my data to give me my most up-to-date knowledge possible. So I'm grabbing only the mean. There are other values given out by the summary, but it gets to be a lot. If I'm not going to be rolling up my sleeve and digging in, I'm just going to leave it for the time being. And I'm doing data prep to get everything set up. So I need to get the parameter value. The parameter value involves the parameter name of theta or tau. It gives the subject number, the row name that is, and it gives the time. Well, I need to separate these three values out, which identifies what it is, and then I have to connect that to the actual parameter estimate. And so all of this is just going through and extracting that off of there. And so this is just data prep, and you can see that I'm doing a lot of string R functions. After I'm done with this, you can see I get a histogram, and here are the individual values. So tau 2, it's 1 every single time. So this really, this is not meaningful for my inference, and that's because of how the model was set up. But I can see the thetas, how on average they change over time. You'll notice that there are fewer extreme values at T1, but as time goes on, we can see that more people are moving to the right. With the theta, a larger theta, we interpret that as the person is willing to take more risky behavior. Now, next thing I want to do a spaghetti plot on the time series to take a look at what's going on. Right now, I went ahead and I colored it by their initial value, their initial parameter value, so we can see. So up top, it's the lighter color, down low is darker. All right, so the larger theta values correspond to riskier behavior. So higher up, that is the riskier behavior, lower down is less risky. So from a public health point of view, we would want to be reducing the subject's theta over time. Now, something that strikes me about this is that there's a pretty consistent trajectory after T2. So whatever we get from T1 to T2 off of the spaghetti plot, that's generally the trend overall. It's not like it goes up and then goes down. It's if it goes down from 1 to 2, it keeps on going down. If it goes up from 1 to 2, it tends to go up overall. Now, and you can also see that there's some pretty hard dark values that are just going down. So the lowest values at T5 were the ones that were the lowest values at T1, and they just continued going down. So this person probably, these people probably just had one, at least one value on the first questionnaire and had all zeros following that. And now, something that is interesting is that when I look at the most extreme T1s, they're going down as we go from left to right overall. So that's, now it's not 100% true, like this person here, but things are not going really that extreme. Like I look at all of these and they tend to go down. All right, so that tells me that there are maybe that person was just going through like a hard time and was doing more alcohol, drugs, and cigarettes early on, and hopefully broke away from that. All right, well, that's all I've got for you. Take care and goodbye.